Okay. Well, my name is Randall Potter. I'm with Drysteam today, and I'd like to talk and present about protecting artifacts and patrons with proper ambient moisture levels in the museum. So today I'd like to talk about really go over what's the purpose of a museum, of a gallery. What are some of the challenges that these institutions face? Preservation of artifacts, and then also the environmental factors that contribute to that. What is the relative humidity and how does it affect artifacts as well? Challenges also due to COVID and the current epidemic, and what can museums do to ensure the safety of its staff and patrons? And then what is the impact that relative humidity can have on reducing the potential transmission? What tools and equipment are available out there to look at? And then how should humidifiers be applied in these environments, or what are the different options? And then some tools and discussion about the things that you may need when looking at designing a project, and then who can help you with this process. So what are museums and galleries exactly? Well, if we look at the definition here, museum is an institution devoted to procurement, care, study, and display of objects and lasting interest of value. It's also a place where objects are exhibited. A gallery, sometimes museum and galleries are used synonymously together. The gallery, looking at the definition there of a room or building devoted within maybe a museum, exhibiting works of art, can also itself be an institution or a business which exhibits dealing in works of art or collection or aggregation of artifacts. So they can kind of be used hand in hand, and so if I use the term gallery, I'm meaning museum, and likewise. So what is the purpose of these buildings? Well, museums are institutions that are housed and traditionally been housed to care for collections and artifacts and other objects of scientific and artistic and cultural or historic value of importance. A lot of times museums will have temporary exhibits, traveling exhibits. They also have their permanent collections. And also museums will have a majority of their artifacts either archived or in research or in studies. So they're not necessarily available for public display or exhibit. Museums are also very important as a public and private center for social interaction and engagement. And this has been the evolution of museums from its traditional role as just an archive in essence, but now it's an engagement through educating and awareness, a cultural development center. It serves as an incubator for furthering ideas and thoughts about the world around us. Again, there's temporary exhibits for this, there's permanent exhibits for this. A lot of these exhibits are engaging, interactive type exhibits. So museums are just as much about its patrons as it is about the artifacts. The challenge that a lot of museums face or galleries face is the deterioration of these artifacts, depending upon what they are, what they're composed of. They interact with the surrounding environment and things in that environment that can affect it. Effective preservation of museum collections and temporary or loaned artifacts is assured by providing a consistent and optimal environmental condition within the building. Helping protecting these various factors of deterioration and environmental challenges can be looked at through some of the factors being temperature, relative humidity, light, pollutants within the air and toxins within the air, or even gassing of compounds that may be inherent in the object or artifact, and then chemicals within our own environment in the air around us. For instance, corrosion can be from oxidation, the oxygen within the environment. So there's a natural process by which objects reach a state of physical and chemical equilibrium that we'll look at as well. So what is relative humidity? What is it? How does it affect this process of deterioration? And how can we work to prevent that deterioration? Humidity levels cause chemical and structural change or physical deterioration to artifacts. High humidity levels can be just as detrimental as low humidity levels. So I know we're here from dry steam, but really what we're talking about is the proper levels to maintain within these facilities. High humidity can promote chemical reactions. Many of these chemical reactions require water to happen. But high humidity also encourages mold spore growth and biological threats. And then if your objects are of ferrous or non-ferrous metals, they can cause oxidation, rust, corrosion. Low humidity, obviously, too, can be just as detrimental, causing organics within an artifact to become brittle and crack. Embrittlement of fibers can cause it to disintegrate. There can also be desiccation, where, in fact, the article or the artifact can be a dehumidifying process, which can cause fractures, peeling, cracking, shrinkage of adhesives. So we're not just looking at organics, we're also looking at other non-organics such as latex and other polymers as well. But I think really what's more important in this discussion is it's not whether the humidity is high or the humidity is low, but inconsistency and instability of what the relative humidity is in the environment and what the temperature is, because temperature has a direct correlation to humidity. We'll get into that in a moment. Causes of instability with inconsistent relative humidity can cause shrinkage and swelling. Unconstrained organic materials can also crush and fracture laminated objects or other types of organic materials within objects. Layered organic materials can delaminate and can also promote loosening of joints and fractures in materials as well. So let's look at relative humidity and what that relationship is to temperature. Relative humidity is a term described to show the amount of water vapor as it is to a percentage of what that air can hold. So the example here shows 30 degrees and 30 degrees representing the size of the vessel. 80% RH would mean that 80% of that air is saturated with, or it has moisture. The content level is 80%. If we take that same amount of moisture and increase our air level to 70 degrees Fahrenheit, that same amount of moisture only correlates to be 18% relative to the volume of what that air can hold. So the relationship of temperature and relative humidity also impacts the percentages, as you can see, by very small amounts. So 1 degree of temperature change can affect the relative humidity as much as 3%. So absolute and dew point are independent of the relationship relative humidity and temperature have. So controlling the temperature within the environment is really just as important as controlling the humidity level. So when we look at materials and we look at what conditions they should be stored at or how much moisture a particular artifact requires, we're looking at the absorption and material equilibrium. Basically, where is that article or that artifact sustained? Depending upon the environmental conditions, some artifacts will absorb moisture, some will adsorb moisture. When we say absorb, we mean to soak liquid up. When we say adsorb, meaning to collect gas. So in this case, humidity is grains of moisture in the gaseous state. So to adsorb it would mean to collect that moisture, that relative humidity, the grains moisture in the air to the particular artifact. Each artifact has its own individual environment, and that corresponds exactly to its needs. Too high, the artifact, it could rot, go into hydrolysis. Too low, it could, again, desiccate or dry rot. So what are the appropriate levels for artifacts? Well, there isn't one particular level. Each artifact will have its own level. The adsorption and material equilibria, or its sustainability, is really dependent upon the composition of what that is. But we can look at that in charts and curves and see where a particular item, material, organic, would find its balance. In other words, we're looking to identify the balance of moisture for a given material that maintains its equilibrium. So looking at some materials, now these are just ranges that are a bit generalized. Specific ranges or specific materials will have a more defined range. So we talk about inks and dyes, wood, ivory, paper, things that may be in an artifact or the composition of an artifact. They all have their own specific range. Again, these are generalized ranges. It's going to really be determined based on the specific material being used, the age of that material, the level of decay or deterioration it's currently in, the material's composition will also determine and require more defined requirements and thresholds within a given artifact. For example, here, the Declaration of Independence, for example, the ink on that, the cellulose from the paper itself, they each need to be stored at appropriate level of temperature and humidity, which will extend or preserve its life. Last thing we want to see, I suppose, is the ink fade away on the Declaration of Independence. So let's look at a particular example. And in particular, let's look at animal tissue, leather, and fibers. So in the, up to recent times, leather was used as a predominant binder or fastener or joiner of many materials and things versus plastics that we use today. Now, preserving these types of artifacts, leather can be used in everything from buttons to clothing to containers, luggage, saddlery, you name it. There's a lot of different artifacts. But if we look at 35% or below, leather shrinks and it can desiccate, causing cracks and eventually disintegrating to dust. It depends, back then leathers were dyed and treated and cured with a different process than today. Today we have a lot of different synthetics that are applied, which prevent some of these things from happening with modern leather tannery. But before modern tannery, some of these do not preserve the leather as well. So if we have humidity levels too high, 70% or above, there's potential mold growth, which will feed on the proteins and the fatty acids, breaking down the very structure of the leather. Also, excessive moisture, perhaps full saturation or even submersion, can create hydrolysis. And what the effect of hydrolysis would be the protein chains that form the collagen fiber, resulting in shrinkage and eventual liquefaction, decomposition of the chemical compound or structure of the leather. And then even worse than too low or too high would be an inconsistent level, because leather is often used sewn in or riveted to other materials, and the response and changes of an inconsistent environment could lead to cracking and splitting and other things. So that's just one particular example. So we've discussed, our artifacts and the relative humidity and the importance of that in preserving artifact. But now museums are challenged with preserving the public health and safety of its staff and its occupants. as well. Some of these risks, if we don't look at what the indoor air quality is and the potential transmission that can happen within a particular place, shut down, staff and patron health and safety, defunding, lost opportunity, traveling exhibits, loan artifacts, and many, many other risks that are involved with this. So typically we look to ASHRAE for guidance. What should a facility do? How do we reopen? What kind of plan, what kind of strategy do we make? Well, ASHRAE, unfortunately, really is only focused on predominantly ventilation in its epidemic task force and the recommendation, which is a bit ironic because when we look at just the mere definition of what air conditioning is temperature, it's ventilation, and it's relative humidity. Those three components make up air conditioning. If we look to a more specific definition of it, the Merriam-Webster dictionary, in fact, says to equip such as a building or vehicle with an apparatus for washing air, controlling its humidity and temperature, also to subject air to these processes. So we need to look at all the things that make up the air we breathe. So proper relative humidity levels shouldn't be ignored, even though ASHRAE isn't specifically saying you should humidify to between this and this. But if you want to look for more information, I encourage you to go to the ASHRAE.org website, the technical resources, building readiness team, and there you will find a lot more information and articles of discussion. But one thing I do find ironic here is ASHRAE has made a recommendation for animal laboratories, which is between 30 and 70% relative humidity. So why haven't they made a recommendation for public spaces? I mean, they make the specific recommendation for mice, rabbits, chimps, but not people. So maybe if the animals would wear their masks or keep 6 feet apart, these facilities wouldn't have an RH guideline. I don't know. So what's interesting too is we look at ASHRAE, and in 85 they have the study that ASHRAE does use for recommended environment and a percentage of relative humidity. And through the Sterling chart published in 85, they recommend 40 to 60%. And I think most of us probably have seen the Sterling chart on multiple occasions, but this has been the go-to for ASHRAE. So my question is, why haven't they reissued the Sterling chart for the epidemic? Anyway, there's lots of evidence, there's lots of studies to show that relative humidity has a correlation to the spread of airborne aerosol pathogens. I'm not going to suggest or say that relative humidity and the level that you keep it as the silver bullet to prevent transmission. It's not. But it should be part of a strategy used with filtration, used with UV radiation, and other means as well. So those are just things to consider. As of just yesterday, the sciencemag.org even just published a new study, another new study. And in their study, they specifically say relative humidity, RH, affects their transport and viability of viruses they contain. What are they talking about? Aerosols. It even says that mucociliary clearance is not as efficient at a low RH. That influenza virus transmission is favored at a low RH. Again, an example just as recent as yesterday. So one example of a current study was the Mayo Clinic study in preschool classrooms, which was conducted in 2016. And Dr. Ryman, a research fellow at the Mayo Clinic, conducted this study. So what did they look to do? Well, their questions to researchers were, how does humidity have an impact on viral transmission, air particles, fomites, the survivability of influenza, the ability of samples to infect cells and culture, the droplet size, the changes in particle size and distribution, influenza-like illness, and absenteeism of students and staff. So the parameters that they looked at they looked at were calibrating air samples, air pumps, run 150 minutes during class to collect these samples. They looked at students between the ages of 3 and 5 in rooms, and for those of us who recall being a kid or who have kids, we all know how clean 3 and 5-year-olds are, touching everything, everything else. So what they did is they unwrapped school objects, collected school objects, and measured air particle size. Their hypothesis was that increasing the relative humidity of the classroom 40 to 60% will reduce the capacity of influenza to survive in the classroom and spread between classmates as aerosols. Standalone humidifiers were installed in the classroom, and the actual RH levels were controlled at 35% of rooms with humidifiers and 20% in rooms without humidifiers. The results, ironically, are similar to that of the Stirling chart already. So it just reinforces previous studies. But again, we have another study to show evidence. So flu-like symptoms reported, 70% were reported in non-controlled or non-humidified rooms. 30% were in humidified rooms. So it wasn't a cure-all, but there were more in non-humidified spaces than there were in humidified spaces. So a significant decrease in total percentage of air samples containing influenza a trend in a decrease of percentage of paper samples collected, and a significant reduction in influenza A presence for total air and paper samples. So when we look at reopening museums, galleries, there's a different strategy that needs to take place, obviously, with interactive type exhibits and things like that. But when we look at the indoor air quality and the potential for aerosol transmission, preserving patron, staff, and health is just as important as preserving the artifacts. And museums are a wealth of knowledge and information and opportunity for knowledge. So balancing moisture levels within the museum should be a part of the strategy to preserve the health for people in order to enjoy the wealth of all this knowledge. So after discussing now the preservation of artifacts, the role that relative humidity can have with that, looking at relative humidity as part of the strategy for reopening and how that could benefit, let's look at couple, the different types of humidifiers that are available currently. There's isothermal, which is a more traditional means of humidifying. Isothermal means to make phase change from a liquid to a gas by means of boiling water. So it's nothing evolutionary or new, but we have different energy sources to make this happen. One being electricity. There's electrode steam, which is applying electricity directly in the water and using the electrolytes of that water to boil. There's resistive element type steam, which is applying electricity through a resistive heating element submersed within the water to make the water boil. Natural gas and liquid propane are another form of energy that can be utilized through a burner to boil water as well. And then pressurized and central boilers and the distribution network of that can be directly injected in the air supply through branch networks of the HVAC, or it can be applied through a steam exchange process. This is taking that heat energy from the central boiler through a heat exchanger and then boiling water that has not been treated that typically is found within the centralized steam production, and applying that atmospheric steam then into the airflow of the HVAC ducted system. The other method would be adiabatic. An adiabatic is taking water and making phase change from that liquid with the heat energy in the air. And the traditional methods for this are a wetted media, so an evap system, where a media surface is wetted and air is passed over this surface to evaporate the moisture off of that. Also, high pressure atomization. This is where we take water, pressurize it to around 1,000 psi, and push that water through a very small orifice in a nozzle to break surface tension and create very small droplets. So a misting or a fog, you'd like to call it, and those fine droplets are easily evaporated within the airflow. Also, ultrasonic nebulizers are another method where breaking the surface tension of the water is done in a tray with where a nebulizer operates at an ultrasonic frequency, breaking the surface tension, creating very small droplets in a fog, which can be carried through the air and evaporated and collected through that air. The benefit of an adiabatic process is that this water, because it's utilizing the heat energy from the air, therefore has a cooling effect that happens. We've all heard of swamp coolers. We've all been to restaurants or bars or other places where outdoor misting systems have been applied to cool the air around us. And this is the same effect. What happens is that about 1,163 BTUs of heat energy, roughly, depending upon the temperature of that air, is utilized for every pound of water that's absorbed. So in essence, we are getting a temperature drop from that. So if you're trying to look for ways to supplement the cooling of a building or cooling of the environment, adiabatic may be a viable option to consider. So what do these types of equipment look like? Well, isothermal type of equipment are steam generators, steam boilers, through direct district plants or localized steam pressurized boilers, or atmospheric non-pressurized steam generators, where the water boiling from that is atmospheric, meaning just like the pot of water on your stove, that steam is atmospheric. It doesn't have extra energy pushing it through. It's not contained within a closed network or system. So it has the liberty of being transferred through its steam line at an atmospheric level. Adiabatic, some of these technologies, again, they're the wetted media, the high pressure nozzle systems, and the ultrasonic systems as well. So an application of an isothermal system can be indoors and incorporated through being mounted on a wall and directly applying the steam in the localized space. The benefit to that is you get a very immediate effect. You're not reliant on the incoming air conditions and other factors that are with your HVAC system. You're really looking at the temperature in the room environment directly as it's being applied. Larger systems can be incorporated into the HVAC system centrally, either mounted in a mechanical room, on a rooftop, or other means or locations. And it can be incorporated into maintaining the entire building's relative humidity. A typical setup may look something like this. So we have a steam generator, whether this is atmospheric or a pressurized boiler system. It's producing the heat energy, the steam, that can be transferred through the steam piping. And then that steam has to be injected into the airflow of the room somehow. So that's going to be through a dispersion system, whether that's a fan assisted directly in a room space, or whether that's in the airflow of an air handler or a ducted system. Things to note when we apply steam within the HVAC airflow is absorption distance. So that's the distance that it takes for that steam to absorb completely in the air so that it doesn't wet the surfaces of the air handler or the ducted network. So things that we need to consider in applying this type of technology are the entering air temperatures, the air velocity, and the volume of air that you're trying to introduce, the entering air RH, because if the air is currently very saturated, it's going to be more difficult for that air to continue to hold moisture and, in effect, make the absorption distance longer. The type of dispersion that's being used too will drastically change the amount of length or time it takes to absorb that moisture. If we're using a single tube, for example, it may take longer for that steam to absorb than if we used multiple tubes within a dispersion panel. And then the amount of moisture being introduced. If we have a small space or small duct and we're trying to introduce maybe 10 pounds per hour, we might have an absorption distance of 12 inches. But if we have that same small duct and we're trying to introduce 200 pounds an hour of moisture, it may take 14 feet because we're saturating a very small amount of space. So we're introducing a much larger amount of moisture. So those are all factors, and some of the factors that need to be considered when applying moisture in the airflow. So how can we do this for a space? Well, there's one method, primary and secondary applications, where we look at if there's a central air system or air handlers for a particular building and a baseline is added before or for the predominant conditions of the space. That then goes through the distribution network for the building for primary areas. If we have secondary areas that are being controlled through temperature with VAV boxes, we can then add secondary dispersion after that, whether that's a localized generator or whether that's part of a pressurized steam network. Then we can individually control the secondary spaces. If we look at it only as a primary air handling application, and we're just going to keep a generalized relative humidity control, there's different ways to approach this. If we have a pressurized or an isothermal, we probably want to keep our steam dispersion after the heating and cooling coils, because if we apply the moisture after the heating coil but before the cooling coil is operating at a very cold temperature, and we're probably going to be drying out our expensive moisture that we just produced. So it may be more beneficial. However, some of the things that we need to consider again is that absorption distance. If we're going to be introducing 55-degree air upon a steam dispersion, it may take longer to absorb that moisture. Another method, if we're looking at adiabatic and we're using high pressure, is that we may want to have that set up after the heating coil to use that heat energy to absorb the atomization of that moisture quickly before the cooling coil. What ends up happening typically when we look at adiabatic is that as we get closer to the saturation curve of that moisture being saturated, it becomes more difficult to add moisture. It makes it very difficult to hit saturation using an adiabatic system. So when we're looking at the cooling coil, we may not be drying out the air nearly as much, but we do need to consider the factor of what this distance is between a heating coil and the cooling coil when looking at an adiabatic solution. Also, we can look at it after the fact of applying it within the duct as well in a more localized space or after a VAV box, if that is the type of application. So energy is a big consideration in what type of system, but there's also other considerations. But looking at energy and sustainability, how much energy are these systems going to consume? And so if we look at generating steam through electricity, then we're looking at about 340 watts for every pound of moisture that we're producing. If we look at ultrasonic and compressed air type systems, now we're looking at about 22 to 24 watts or 75 to 82 BTUs an hour and per pound. And if we look at high pressure atomization, we become more energy efficient where we're looking at only 3 to 4 watts per pound of moisture being applied. Evaporative media is the most energy efficient when we look at these methods, where we're using typically less than a watt of energy per pound of moisture to be evaporated in the airstream. So everything has a benefit and an adverse. The evaporative media, the benefit is the high energy efficiency and the cooling effect that can be gained from that. The downside is that it can be very difficult to control our plus or minus output with an evaporative media system. So those are just some things to bear in mind. If we're looking at using evaporative media to sustain a baseline range within a building and then applying a secondary system in a more localized environment, that may be a more energy efficient way to approach the project. So when we look at adiabatic and air handling application, there's direct and indirect evaporative cooling that can be set up or that can happen. Indirect, meaning that we're not going to be introducing that moisture within the space, that the moisture is really being applied more for a heat exchanger and cooling without adding that moisture into the environment. Direct evaporative cooling and humidification means that we would be taking that air, and the air that it's cooling is also going to be the air that it's humidifying, which would be applied directly in that room space. There's a few different ways to look at using adiabatic technology and how it gets applied within the environment. When we look specific,
we have a question in the questions tab for you.
Do we have data for gas-fired systems? Yes, I believe we do, and we can certainly get that addressed. So I will answer questions at the end, just so that we get through the presentation first, if that's okay. So we look at wetted media and energy efficiency and cooling. It can also be a lower maintenance type of approach as well. And in certain instances, LEAP credits and utility rebates may be an option for this type of technology. Typically, it has a lower upfront first cost, especially when applied through an air handling manufacturer. High pressure atomization is dispersing within the air handler or the ducted system, dispersing mineral-free water, high pressure. Again, that high pressure water through an orifice or a nozzle, which breaks the surface tension, provides both the cooling of the temperature and the relative humidity. The benefit over high pressure over media evap is its ability to be controlled very tightly. So the output can be controlled in this type of setup. However, there's a lot more infrastructure involved typically with high pressure atomization versus media evap. So we're looking at dechlorinating the water, removing the chlorine, softening that water and displacing the carbonates, the hard minerals with soft minerals. This will extend the life of an RO membrane. There's an RO system, which then has a buffer tank. And then we have a high pressure pump. Now the high pressure pump can distribute to 4 different air handlers or 4 different zones, which can then be staged and regulated to modulate based upon the demand coming from those. So we have solenoid valves, which will control the output based upon what that signal is coming in. But whether we look at isothermal and whether we look at adiabatic, humidification all begins with water. And so what is in the water and the constituents that make up that water is really important to the longevity, the maintenance, the life of the system, and the performance of that system. So the 4 types of water that you can use are potable water, softened water, reverse osmosis water, and deionized water. We do not recommend using well water. There's too many constituents and too many other types of variables involved with well water and inconsistencies. And so we do not recommend the application of well water. Why is the quality of water important when humidifying? Well, the 3 key goals on preventing maintenance and things are water through the goals through water treatment are to prevent or reduce the amount of scale, to prevent fouling, and the hygienic aspect of preventing bacteria and algae growth. So when we look at water and humidifier maintenance, we can see examples here of hard water form scale and regular maintenance that would need to happen. Now, when we use soft water, soft doesn't mean that we've taken minerals out of the water. It just means that we've displaced the hard minerals, which are your carbonates, your manganese, your fluorides, things like that, now with sodium. or potassium. And this may extend the maintenance intervals by a factor of 3, but there is still maintenance involved with that. To completely reduce the maintenance for up to very long intervals would be to apply reverse osmosis water or even deionized water. And these systems then alleviate the maintenance from the humidifier, typically to the water treatment side of things. So with water, you can't have something for nothing. There really isn't a free lunch, unfortunately, with water. And anyone who's worked with cooling towers can understand this and appreciate this as well. Humidifiers are very much the same way. So how do we maximize operating longevity with water treatment? Well, again, we need to look at the water source. We need to understand the water quality and what impact that could potentially have on the system. When there is cleaner water, so reduced minerals out of the water, there's more uptime or more operating time possible with the unit. And one of the other factor is what water source should be used. It depends upon the type of humidifier and the compatibility as well. For example, if you're using a system with copper heat exchangers, you may not want to use deionized water, as deionized water can be very corrosive to those types of non-316 stainless steel type humidification or heat exchangers. If you're atomizing water or even using evap, you may want to use reverse osmosis water. The idea is if we're using a high pressure system and we're applying this atomized water or atomized vapor in the airstream, we want to remove those minerals because it's the water that evaporates, but the minerals remain. And when you're spraying it or fogging it, it creates dusting. And this dusting can lead to a lot of other havoc later on. So pre-treatment's really important in the approach on adiabatic. If we're looking at media, can create fouling and scale buildup, increasing the pressure drop of the system and leading to challenges related with that. So when we look at the project design and the sizing and selection, what are the tools out there and what are the things that we like to look at or need to know in order to size and select and lay out a project appropriately? The entering and leaving conditions, the volume of air, the air temp, the percentage of outside air is very important, which I'll show in the next slide, and what that relative humidity is coming in. If we're in Miami, Florida, it's going to be very different than if we're in Tucson, Arizona, for example. Also, the water quality, understanding what the water quality is that we're working with. The absorption distances available, whether that's in a ducted system or an air handler. How much distance do we really have to work with? And we also need to take into consideration, which I won't discuss in this presentation, but elbows, transitions, sizing changes, things like that in the airflow. Those are all important factors to consider and understand when laying out a humidification system. Also, what's your load going to be? Understanding how much moisture that you're going to need to apply, whether that's the nominal load or the peak load. Those are things that need to be considered. Also, what are the maintenance needs and requirements? Of course, everybody wants the maintenance-free humidifier, and I'll be a billionaire the day that I invent it. So what we have thus far is really alleviated to the use of deionized water is probably the most maintenance-free that we can get with a humidifier as it sits right now. But determine the steam source if you're going to use a centralized system. If you're using a steam source off of a boiler that's highly treated with chemicals, it may not be the most appropriate steam to introduce into the occupied environment. A steam exchange process may need to happen for that. And then plan the control system. How are you going to control the system? Is it through a building automation system? Is it a localized demand signal? Those are factors that need to be considered as well. And the tools available for this, you can also look at registering for dry calc if you're not currently set up, but that's pretty easy to find through drysteam.com. And it's a very easy process. And there you'll find some tools and things where you can look up energy calcs and load calcs as well. So as I was mentioning, it's important to understand how much outside air we're going to use. So an example here, and if you're going to use economizer mode as well, we look at the outside air intake rate at 24.4. We look at a load of basically 65 pounds an hour for this example. It doesn't matter what part of the country or world we're looking at. This is just an example. But if we increase that air to 100% outside air, and such would be as an economizer mode, we've increased our load to almost 200 pounds an hour. So these are just factors that need to be considered. And we all know that what happens in our designs as engineers don't necessarily correlate to what happens in the field. So just bear in mind that if you do have a system with an economizer, take into consideration what that load may look like during those months. And where else can you get support and help? Well, we have a wonderful and very responsive rep network. And if you're looking for who your localized rep is, you can find through our website and enter in a zip code or country code, and you'll be able to find your localized support and rep. We also have BIM object available through RCAT, through the National BIM Library, and also specified by as well, where you can find the specific products and help in your layout process. And with that, I thank you for your time, and I will take questions and do my best to answer them. If you have questions later on, please feel free to email sales@drysteam.com, or again, look up the localized rep. And if you'd like information more on the technical aspects or details, we can certainly get that information to you. And our regional sales managers are continually traveling to go and explain and help with design process or existing sites or challenges that may be in the field. So please feel free to utilize them as a resource as well. So let's see some questions here. Again, on energy and sustainability, do you have data per pound for gas-fired systems? I believe we do, and I can forward that to the appropriate person and get that answered. I think we can even go so far to look at a specific example for that. We can get some further information, Abby, and address that one. Another question here. So evap cooling, yes, looks to be more energy efficient, but do we consider the amount of heat we have to add to the air to get that absorption? That's a great question. So if we look at the amount of energy it takes to make phase change of water from liquid to a gas or a vapor, it takes more energy to do that process than it does to increase the heat of a heating coil to evaporate that moisture. We can look at a specific example if there is one and have that addressed. But typically that, yes, it's more energy efficient to increase a heating coil if there's added capacity, or even add a second heating coil to absorb that moisture for the adiabatic process. And do you have to heat more with an adiabatic humidifier? Well, I don't want to say yes or no, because it's really application dependent. If you're in a very dry climate, you may not have to. If you're in a more humid climate, or a climate where the winds can change and you may get coastal moisture, and for example, like Santa Ana winds in California, you can go one day within a few hours of being at 65% RH and 80 degrees outside for your outside conditions, down to 90 degrees and single digit, 9 to 12 or 10% relative humidity, just in a matter of hours. So depending upon, some other factors will determine whether you need to preheat more with adiabatic. How does RH correlate to library archives? So relative humidity, if we're looking at library, I'm assuming this would be like books and photographs, library type materials. It's going to be dependent upon what those specific materials are and what the isotherm of adsorption would be to properly store. We don't want to add excessive air moisture, and we don't want to have a lack thereof of moisture. An example, maybe library archives as well, would be things such as vinyl records and that type preservation. When preserving artifacts, is it better to control RH or dew point over varying temperatures? Good question. I think it's really dependent upon the environment. If we're talking about cold storage or very cold temperature type archiving, it may be much better to control with the dew point, considering that the dew point and the humidity level could have a big impact on what's being stored. If you're looking at traditional room temperatures and things like that, then controlling RH is probably sufficient. It really just depends upon the particular item and artifact being controlled. It looks like we just have a few more minutes. Any further questions?
Alrighty, if you don't have any more questions.
I appreciate everyone's time and hope that some useful information was able to be gained from this. I believe, Abby, we are offering PDH or credits.
Yep, you will receive a PDH certification with your follow-up email, which will also have the survey and the PDF form of the presentation.
Okay. All right. Well, thank you for your time.